Right, good evening everyone. Thanks for joining us for the third Sheffield Devops since the event. I don't know how many in total there's been, but there's been quite a few. We are streaming this evening, so if you have any questions on the stream, you can drop them under the video on YouTube or on Slido using the hashtag Sheffield Devops. There's someone from Slido in the room this evening. It's not sponsored by him or anything. The look of surprise is just given when I said we're using Slido. People use it. Yeah, people do use it. So thank you to Sky Betting and Gaming who are hosting this evening for the pizza and drinks, etc. Thank you to Effecto Recruitment who are sponsoring the stream. And finally, thank you to David, who's going to do an amazing talk, I'm very much assured, on Redis in about 10 seconds when I've shared the slides on the screen. Okay, cool, thank you.
Right. Good evening. I am David Lockwood. I'm lead engineer at Useful, and I'm talking about an application that my loyal team and I built, and an incident that we had in it, and sort of what that looks like, and what we learned. So this one I'm going to talk about. So I'm going to sort of give a bit of background of what we built, why we built it, and who we are. I'm going to sort of give you a bit of an overview of the architecture of it. I'm not really sort of here to talk about the architecture of the application specifically, but you kind of need some context to know what was happening and why. I've also cut out quite a lot of the complexity where I can, so it's a bit of a simplified view, so there is more going on than I do show. Then I will talk about the incident we had and how I responded to it, some of the metrics we looked at and what we learned sort of poking around into it, and eventually what we did about it and why that made sense. So this is useful. We're a relatively small company, relatively young. We are involved in one-to-one tuition, so we sort of match tutors and students for one-to-one private tuition. And this is our vision. Teachable is the most trusted name of learning, and we use technology to make learning for the best educators around the world accessible to everyone. So as part of that, this is what I've been doing. So this is an online classroom that we built with me teaching my user lots of interesting things that he definitely understands about coding. And this is the UI for it. And it's there's whiteboards, there's video, there's chat, whatnot. And a student and tutor will go in here to have their lesson and interact and have a great time. You'll have seen similar things to this, and there's lots of similar kind of products that do these kind of things. We decided to build our own specifically. We had tried some of those third parties, and I mean they were okay, but we were kind of dissatisfied with them in some way each time. And there was fairly limited integration we could do with our platform. So we could send them there and they could do it, but we didn't really have much control once they were in there. We also couldn't really respond to what our customers wanted and what we wanted to do with it. And so if they asked for something, we couldn't really directly do that. And if there was a problem, we'd pass it on to the people and hope they did something about it. And even though we're a small company, but there's quite big ambitions there. So if we build our own, we can control it, and we can build those ambitions. So there's the reason for it. I sort of mentioned scale at the start, and this is not this global multinational sort of huge application, but so I'm talking about scale. This is kind of level we're talking about. So for the last 18 months or so, we've been getting more and more users using our platform, and so at peak time we hit around 1,500 concurrent connections. So it's not like absolutely massive, but it's not a tiny insignificant number. So the main sort of chunk of it, a really big part of this is that communication between those two different clients, so that student and that tutor. And so we use Socket.io for that. So we need some way of sending those messages from one client application to the client application, and that might be a chat message, or when one user draws a line, the person sees a line, or whatever interesting thing they're teaching. And Socket.io gives us that real-time communication. So this diagram, I'm going to keep referring back to this because it's quite useful, but it's ripped entirely from the Socket.io docs. So you have some client applications, they connect to some Socket.io servers, and then there's Redis doing something around helping these Socket.io servers communicate. Our kind of station of this is we've had to build some code. We have our client apps, so you saw that was a super pretty picture. And then we have, that's opening a socket connection, doing a bunch of other stuff to our pub app. So this is a Socket.io server. I mean, there's a bunch of other things it's doing that are quite specific to our needs. So it's more than just a Socket.io server, but like the purposes of this talk, you think of it as Socket.io server. We deploy all this in AWS. So our client apps, we push it to S3, we serve that behind CDN, and our these Socket.io servers, they're Node, they're in Node, and we bundle those up, build them in the Docker image, and we deploy that to the AWS Elastic Container Service as Fargate tasks. They live behind the load balancer. They also scale magic. Then Redis is just ElastiCache, Amazon's ElastiCache for Redis service. So the title of the talk has Redis in it, and I'm going to use Redis a lot. So I always assume kind of most people know what you're talking about. When you work with something like, you kind of assume everyone knows about it. But just in case not, I've got a few helpful definitions. So Redis is fast, open source, in-memory, key-value data store, and it delivers sub-millisecond response times, enabling millions of requests per second for real-time applications. So it's fast, it's in-memory, and it's real. We use ElastiCache Redis. It's fully managed and caching service with microsecond latency, so fully managed, so it's not our problem. And it's microsecond latency, so super fast. You can have Redis in two kind of configurations. You can have a primary node with a primary-replica architecture in a single node primary, or a cluster topology. So you can deploy it as a primary with 0 or more replicas attached, or you can deploy it as a cluster. For reasons, ours is primary with a replica. So that's sort of the background of the way. So I'm going to talk a bit about the incident that we had. So you can cast your minds back to November last year, when it was dark and it was wet and it was cold. It was a simple time. You could afford energy. You could feed your family. It was great. So this particular day, November 22nd, we started getting these automated alerts. So when we first started building this application, we set up some alerts just to, tell us, when we were hitting the limit of something we knew existed, or something unexpected was happening. One of these fired, one of these was, oh my god, Redis has got a lot of high memory use. And it's like, oh, this is weird. And so we poked around the metrics, looking for something, and didn't really see anything that we knew what to do with. We looked at the feedback that we got after each lesson, and no one said anything was wrong. And we talked to our customer service team, and they were like, no one's complained about it. It's like, oh, that's weird. And so we kind of wait to see what happened. And it happened again the next day, and again the day after that. This is always in the evening. So this is a random week I've chosen, and this shows the sort of the number of lessons that we have on. So we have Monday, Tuesday, Wednesday, Thursday big spikes, and then Friday, Saturday, Sunday drop off. So if we have this problem on Monday and on Tuesday and on Wednesday, probably going to have it on Thursday. Thursday's getting fairly close to the weekend. I don't really want to have my weekend ruined, so we should do something. So we decided to try and do something. So 25th rolls around Thursday. And what we've learned running the system is that if anything goes wrong and there's any kind of problem, it's here. Like, this is the bit that all the communication goes through. And this is the thing that is most under load. And so if it's under load, what we do is we make more of them. So we just reduce the scaling rules. And so more of these Fargate tasks, these Socket servers exist, and that just gives you way more headroom and resource just to deal with any problem that might come up. So we did that, closed our laptops, confident that everything was going to be fine. But the title, a bit ago, was the incident, so it clearly wasn't fine. So a little bit later that evening, 5:23, our customer success team started getting calls at the classroom, quote, wasn't working. So that super helpful phrase that torments everyone worldwide. Wasn't working in this case meant really quite slow. So that's not good. So we kept calm, clearly. We were fine. And so the decision we went with was, so, we had this problem, and we saw that when we increased the number of tasks, that kind of made it worse. So clearly, the obvious thing to do next was really double down on that decision, increasing even more. So we did that. Hindsight, perhaps not the finest thing we could have done, but so quite a short period of time after we did that, it was quite clear it really hadn't helped, and things were, at the very best, not better, but realistically significantly worse. And we'd gone from this, it was very slow, and it wasn't really doing much, to just, nothing's working, nothing's communicating at all, and the phone's going crazy, and it's like, this isn't great. So our account at this point turned frosty. Like, we were very chill at this point. So the decision we went with was, if adding more made it worse, we should have less. So we did that. So we looked at the data the last few weeks, and it's like, we reckon we could get by with X many tasks and cut it down to those. And at the same time, we have some high frequency messages that go through. So one of the types of messages is mouse movement. So you see the person's mouse move as you're moving, and people like to move their mouse quite a lot. So quite a lot of those messages go through. So we reduced the number of those. And those two things together helped. It's great. Everything came back. So we can relax. Great time. Problem solved. So we spent some time after that trying to work out what had happened. So we hunted through some metrics. Don't worry about squinting at those. I'll go through those later on. And we observed, I won't say determined, we observed that there was a really high memory usage in Redis and increased memory fragmentation. And we could see, interestingly, that the CPU wasn't under much load, so it maxed out about 40%. So the thing I kind of looked for at first is if memory shoots up, it's like, is garbage collection being blocked by the CPU? It's like, nope, that's not happening. So that's kind of weird. And at some point, memory went so nuts that it just overflowed the swap, and that's when things really started getting slow. And we poked around. We could not work out what the actual cause of this was. It just seemed to come out of nowhere. So this was our conclusion. We hit some sort of tipping point. So whatever happened, it just suddenly hit this point, and it just couldn't manage, and this led to this cascading failure. There was a backlog of messages, and just eating through this required even more of whatever was constrained, and it just made it worse and worse and worse. And we tried to replicate it on our staging environment, and we tried to load test the hell out of it, but nothing. Everything was fine. But we did discover an operating procedure, and so we're experienced engineers. We've seen a thing or two. We've been around the block. We've done things. We know how this thing works. So you have a problem with a computer and it's not quite working right, you turn it off and on again. We all know this. So we turn it off and on again. So into AWS console we go. We head over to our ElastiCache page, head to our replica, give that a reboot, head to the primary, fail over the primary, which promotes the replica, and jobs are good. And we have our spanking new Redis instance ready for use. So we were left with quite a few things that we didn't really understand. And the phrase we're kind of setting on, what's the smoking gun? What's the thing that is just triggering this? Like, what's the metric that starts for everything else? What's the pattern that everything correlates to? And we just could not find anything. And we didn't understand why increasing the number of those Fargate tasks made it slower, because like everything that we've been taught is just that the more you add, the faster everything gets. But in this case, the more you add, the slower it gets. That's weird. Inversely, why does adding less make it better? It never happens. This is weird. The big fear was really, it's like, have we done something that this is just how we operate our system now? Do we just have to turn it on and off again every now and then? Have we done something like that's just lurking in there that this is what we do now? we just didn't know. And so we put all of this knowledge together, and we came up with a prediction. So one prediction was the Redis box we chose is deliberately quite small. So we chose the smallest thing we thought we could get away with. And so it's probably that. But we don't really know if it is. We don't know why, because all the metrics kind of look fine. Apart from memory, there seems to be lots of headroom. And we could just make it bigger. But we don't really know why we're making it bigger or what specific bit we're optimizing for. This problem is just going to be lurking, and it's going to come out at the most inconvenient time, and it's just going to ruin your life at some point. So let's not do that if we can avoid it. And we also thought that we went with the operating procedure theory, and it was, this might happen again, probably not going to happen regularly. So let's see what happens. And if it does, don't worry, we know how to fix it. So this is going to be fine. So we confidently, we talk to engineering teams like, don't worry, guys, it's fine. We know what we're about. It's great. Talk to the company exec team. It's like, it's fine, guys. We've got a sense of control. Everything's fine. And it wasn't fine. It wasn't fine at all. So Christmas rolls around into the new year, and sort of sometime in January, it happened again. And I point out like that the first example I went through, that was the worst, the worst possible way it went. So at this point, this was about half an hour maybe of degraded performance. And no root lessons were ruined. No one just couldn't use it. It was just degraded. But it didn't happen. It didn't happen once, and it didn't happen twice. Over the next 2 weeks, it happened 5 more times. And by that 5th time, we were getting quite apprehensive because we had to do something. We just have to do something. This is users' experience being affected. The business being affected. We have to try and do something, and it has to be quite quick. We're experienced engineers. Like, we've been around the block. We've seen things. We know how this works, and we've tried turning it off and on again, and that didn't quite work. So there's only one thing left, and that's just make it bigger. So the thing we didn't want to do, sorry, Boromir, we scaled it up. And we just went up size, and for the next few weeks, everything's fine. And, it's fine. As things do, as soon as something stops screaming in your face it's a problem, it drops off your list of priorities, and it goes from that thing we have to do to that thing we should do to that thing that I will do when we have time. And so we it wasn't playing anymore. One screen was everything was looking okay. We forgot about it. Not forgot about it, but pretended to. And about 6 weeks went by of no incident until the incident. The day of infamy, 5:55 p.m. Tuesday, 14th of March, 2022. Tell your children about it. It happened. This is the one where we took off our kiddie gloves and actually tried to, fix the problem rather than sweep it under the rug. And so this is one where we delved into sort of the metrics the most. So I'll step through the incident, sort of what we saw and what we looked at. And you can kind of tell a story through the metrics of what happened. I'll try and do that. And so the things we're looking at, so that's this diagram. Some of these will be pulled out from the socket O servers and the Fargate tasks, some from the Redis instance. So I'll try and identify which one. So the first bit you see is everything starts to build up. So we get CPU, Redis, CPU network, they have to go on and just crash and go nowhere. Memory, that similarly starts to climb, replication line starts to climb all at the same time. And then the number of connections spikes. So number of new connections spikes. So the number of current connections climbs at a fairly similar pace to the task count. There's just more tasks are created, they open more connections. But then suddenly, at around the time of the incident, it's just new connections go crazy. But the number of current connections, they're just the same. So after that, we see some degradation of service of how it's all working. So at some point, you hit 100% memory, and swap kicks in. And when swap kicks in, people are having a bad time. So Redis, the command latency follows a very similar pattern to this swap and connections. So socket connections. This is clients connecting to our Fargate tasks. They start dropping off at an increasing rate. And so we're seeing, Redis is undersphere load, and I've put the line here. It's a bit of a, could be anywhere. It's somewhere between here and here. It's just communications just not going through between these clients. Next, everything sort of rises to a peak. So activity really starts to peak. So number of connections is going nuts. Memory is climbing to an absolute peak. Swap is equally following it. And then we also see the number of messages going throughout the system drops as these all peak. And equally, interestingly, the number of Fargate tasks we have, so this is space and load, is just dropping like a stone, and has been for a while. But then there's this sudden spike of activity. Suddenly network kicks back in and something starts happening, and stuff starts going across the system, and the number of Redis commands just explodes into something, and the number of messages suddenly shoot through the system, and then everything starts climbing. So memory starts climbing, swap starts climbing, replication lag, until eventually we recover with our sophisticated operating procedure of failing over primary. So memory starts to come down. There's a spike of CPU, and then that goes okay. Swap vanishes, replication lag vanishes, and then other bits of the application. So the elastic load balancer goes from doing barely anything to something, and suddenly gets a load of requests that it just hasn't been getting for a while. Network is returning something normal and starting to do stuff. Number of Redis connections is, there's a spike of stuff connects, but then it just continues in a fairly normal pattern. I've chosen a terrible place to put this line, but this is spiking to about here. So the number of new socket connections spikes up and then happily goes along. But then those tasks just continue and it's very low. They don't go back up. So we compare some of these things that are going on to like what it normally looks like when it's operating. So task count. So this is the number of these that are in existence. So you can see that we're starting around 5 o'clock, around 5-ish, like just above 5, and we scale up in a fairly similar pattern to around like 14 at similar-ish time. Like maybe we go a bit faster from the week before, but it's not wildly. It's not like we're suddenly spiking it to like 20 or so. It's not like a huge increase in volume or anything of traffic that's going through. And the same is true of messages. Like we're starting around 50,000 up to about 100,000. We're just under by 6 o'clock. Very similar here. Like maybe it's slightly higher, but really not that much. It's a very similar pattern of usage and the amount of data that's going through the system. It's also slow animation. Number of sockets, like the same sort of pattern is seen in very similar numbers of like above 1,000 to about 1,500. So there's not that much going on that's different. Like after the incident, everything changes radically, but before it, it's all looking very similar. So for recap, what we observed is, we have like normal operations for weeks or months at a time. So everything's fine, and then just suddenly it just explodes, where just things that just normally just do not move, just suddenly just go crazy. But the actual traffic itself is relatively unacceptable. There's nothing that different about it. And we see everything just climbs to an absolute peak, which follows by just everything grinds to a halt and it's barely usable. But we just could not find a strong correlation. So the thing that we were really looking for was some sort of pattern that correlated with something else, and we couldn't really see what that was. We just couldn't find a smoking gun. And the thing that kind of haunted and really held us back looking into this was like, it's a fairly complex system. There's quite a lot of moving parts, and is all the problems that we're seeing around the Redis box, are they the problem? And they're telling us that this is the problem, or is it just a symptom of like something else happening? Like, I don't know, is one of these clients doing something really different and more is going through? So we weren't sure where to start looking. So one thing that we found is, as we were talking about it, we struggled to really describe what was happening in Redis and what Socket was doing. And we kind of needed to learn more about exactly how that works, just to be able to describe the problem properly, just to try and work out where we were going. So we're using Redis because Socket told us to. So Socket is a library, and it gives us that bidirectional communication between our client and our server, and it has an in-memory adapter, and that stores a map of relationships between sockets and rooms. So it has a list of maps of rooms with all the sockets that are in that room, and then a big list of sockets, and it uses those to send it to the right thing. So you have, if you're sending something to a room, it's looking at this room map. If you're broadcasting to everyone, you're using the socket map. And when you're scaling between, you're scaling up lots of socket IO servers, or target in our case. Each one of those socket IO servers has its own map in memory. And so if you have client A connecting to server A and client B connected to server B, neither one knows that this one exists, even if they're meant in the same room. So you need something that knows how to route this traffic. So if we look at this back on the diagram of sending a message from A to E, we can see that client A sends its message up to the server, goes to socket A, checks the adapter, and the adapter's like, cool, we're in lesson 1 together, there's A and E in there, I know where to send it, and somehow it makes its way over to client E via task 2. Magic. Doesn't really tell us, how it works. And so when we dig in, there's a couple of really interesting points to get out. So one is each socket IO server receives a data packet and broadcasts it to its own list of connected sockets. And the other one is no data is stored in Redis itself. So something's getting stored in Redis, but apparently it's nothing to do with socket IO. And also that each socket IO server has its own list, and each socket IO server receives a packet. That's interesting. So let's look at that on the diagram as well. So this time we're going from A to C, sorry. So they're on the same server. So again, we send our message up to socket A. That checks the adapter, and that's like, cool. Yep, I know I have socket A and C in here, and that's all on task 1's adapter, and it knows to route the message down to client C. That's fine. And then we now know that the adapter pings this up to Redis, and then Redis sends that message over to task 2, and its adapter goes, oh, nothing to do with task lesson 1 here, nothing. But both have received the message. And when we dig into the docs a bit more, we see this of Redis adapter relies on the Redis pub-sub mechanism. Now, I've always used Redis as a key value, so I didn't know it had a pub-sub mechanism. So it's like, that's interesting. We should know how that works. Redis is best known for a key value sort. So every time I've used it and everywhere I've worked, it's always been as a cache or database. But apparently in 2010, 3 commands were added, which enables this pub-sub mechanism. So if we look at how it works, we again have a map, a little variable map of channel names, set of subscribed clients. So, and similar to the socket IO maps, but instead of sockets, it's TCP connections. We have our subscribe command, adds our client object to the map of clients, our channel name, unsubscribe, removes it, and then publish. Looks up subscribes on the map, schedule the job for each client, send a message to client socket. And schedule the job jumps out because I don't know how you can schedule something without storing it somewhere. So I think we're on the way to something. So we know Redis pub-sub is good for real-time, low latency urgent messages, which we're using it for. Only connected subscribers receive messages, and every client receives it, and they receive it once at most. And then the really interesting bit, once the message is delivered to all current subscribers, it's deleted from the channel. So something's definitely stored. If something's deleted, it got stored. So we found something that gets stored in Redis. This is great. I mean, it was probably a message. It was always probably messages, but we didn't know it was messages. But now we do. So what we know is, the whole message is getting sent to Redis. And so this isn't like it's not the task asking for, I don't know, where to send this to. It's like, it's just sending it to Redis. And we know that Redis is then sending this to every single task. And so every task is receiving every message that's sent. So the more tasks we have, the more messages we have. So that's pretty interesting. Then we know the messages get stored until they're consumed by every subscribed client. And so if they're getting stored but not deleted, then that's something. It's clearly the messages that are filling Redis, and if they're not getting deleted, it means they're not getting processed, and we can see they're not getting processed because there's less going on the network, and there's less going on the CPU, and there's fewer messages going around, and we can see them going into memory. So this isn't really telling us what the problem is, and it's not really giving us as an answer, but it's we're painting a better picture and start to understand how the system is behaving. One of the things that jumped out that was that spike in connections. We didn't really understand why it was happening, and now we've learned a little bit about Redis. It's something we could come back to and try and work out. So the normal sort of traffic that we sort of behavior we see is we have steady climb, and then we sort of flatten out the number of connections, and then Redis connection stays fairly static of just making some. But then when we have an instant, that same current connection is the same, but we have this huge spike of new connections, and it's significant. It's like 10 times as many. So now we know a little bit more about how Redis is behaving, how that Redis pub/sub mechanism works. We can add to our diagram, and we can sort of look in our code and find exactly what connects to Redis. So we have our Redis adapter. The Redis adapter, if that's using the pub/sub mechanism, that means there are 2 clients for each one. So there's a publish client and a subscribe client. So each one of these is having 2 connections straight away. There's also the replica that I mentioned. So there's some number of connections needed here just to be able to replicate. So there's something else going on there. We have like this main connection, which is used for like a bunch of little things like health check Redis is alive, like an atomic counter, a few other things. That's not a pub/sub, that's a regular connection. And we also have this attendance queue. So this queue is it's also a pub/sub mechanism, and so it also has 2 clients, and that's just sort of keeping track of who's where and updating something else to say, oh, these people are in this lesson or not. And they arrived this time, left that time. So even without trying very hard, we can see there's sort of 5 connections going on here, a number here. So there's quite a lot of places. So we one thing is something about our connection code misbehaving. There's a lot of places if one of those just going nuts is like one of the tasks, like just misbehaving strangely. It's just sort of going rogue and being weird. Just not sure. But we didn't get too far down this line because quite quickly not quite quickly, but at some point, the thing that jumped out more and more, that once you see, you just can't unsee, is just that network drop. Because that line is really flat. It's just weirdly flat. And when there's so many other things going on, it was quite easy not to notice this. But in hindsight, it's really hard not to. So this is the purple is network count, and we have number of bytes across the network, number of packets, and that line is just it's unnaturally flat, and that just suggests that something's been throttled somewhere. So we can check into Redis docs and find out that there is a metric we can check. This metric. Network bandwidth out allowance exceeded. And this tells us the number of packets queued or dropped because the outbound aggregate bandwidth exceeded the maximum for the instance. So this is going to tell us if we were throttled. Great. So we can head into CloudWatch and we can say, hey, there's anything throttled, and it's like, there's nothing there. It's like, that seems unbelievable. I mean, it wasn't actually just that there was nothing there. This was me taking a screenshot after. There was just no metric. And that was weird. So we need to hunt around some docs more. So as I said, we're on tiny little boxes. So we're on T2s, and the network was, you go into the docs and it says low to moderate, which isn't very easy to graph. But we dig around a bit more and we get this. So we find, up to 1 gigabit per second network performance, and then there's something is not supported on ours. So we can find out what that is. And it's like, ooh. The ENA driver provides the cumulative number of packets queued or dropped on each network interface and /track reset. So that's clearly the exceeded allowance metric. And we've managed to choose the one instance type that does not support that. So that was really helpful. So the one thing that would have given us an immediate answer of like, yes, this or isn't the problem, we just didn't have. Anyway, we can put that 1 gigabit on our graph, and it's miles away. but that's really fun. Like, even if it is, I just don't believe it. So we have AWS support, so we might as well use it. So we ping them a message and we're like, hey guys, we have a problem. This is what happens. Can't find this metric, but it really looks like something throttle. Can you just tell us if it's true? And they're like, yep. It's like, great, thank God. Finally found it. It's network throttle. But I still don't really understand why network throttle affected everything the way it did, because so a lot of things were going on, and it needs a bit more digging to really be able to explain why network throttle had those symptoms. So the first one thing to understand is baseline versus burst. All cloud providers will have something like this. So AWS is like, it's not something I'm unaware of, but it's clearly something that we didn't have at the forefront of our mind the entire time. So you get a network bandwidth allowance based on the number of virtual CPUs you have. If you're less than 16, you get a baseline bandwidth guaranteed, and then you get a burst capacity that you get for up to a certain time, so up to an hour, and it's not guaranteed. It's all best effort. And you get it on a credit system. So if you underutilize your baseline, then you earn credits to be able to burst at some point. And the one we were using had a baseline of 0.128 gigabits per second, and it can burst up to 1. So let's put that on our graph, and boom, look at that. Aligns very nicely with our line. So we're on the right track. So one thing that we can definitely see, it's going to be pretty obvious why memory and CPU are behaving the way they are. So CPU is dropping because less is going across the network, obviously. And we know that if less is going across the network, then we know that Redis pub sub has queued up all these things and they're not getting deleted. And so that's why memory is going up. That's great. Not dead sure why replication lag is going up the way it is and why there are so many new connections spiking. So there's something they don't understand still. So as we delve into Redis, the memory or the metric that you get from Redis is bytes used for cache. There are 3 things that Redis uses memory for. So it uses it for storing those key values, those key value items and just its data items. There's whatever it needs for internal overhead, and there is this client output buffer. There are 3 types of client output buffer. In fact, there is a normal client output buffer that does normal client output buffer kind of things. It just hangs out, goes to the park, goes to the pub. There's a pub sub client output buffer, and there's a replica client output buffer. So we know that, so this sounds like something where our messages are being queued, where the pub sub is queuing those messages, it's putting them in the output buffer ready for consumption. So we know something about that. But this replica one, there's clearly something happened in replication, so we should learn something about replication. So the Redis client output buffer, it stores all those writes ready to send node replication, and there's a hard limit which was imaginatively named client output buffer limit replica hard limit, and that is a non-modifiable sort of hard limit of what the client output buffer can store. And in ours it's 166 megs, and when you cross that buffer, you get something called a replica client output buffer overrun, and that results in disconnecting the replica immediately. When a replica disconnects, it tries to reconnect, and it will try and resync. And there are 2 types of ways it will resync. So the first one is a partial resync. So it will just try and pick up where it left off. And it doesn't cost much, and it's super cheap, and that's great. If it fails to do that, it will try a full resync. And a full resync involves asking the primary to snapshot all of its data and then send it over to the replica, which is just the worst thing we could really want it to do right now. Where it's just the things that are under load are the exact things that the replica is asking the primary to do. It's terrible. So when we put this all together, we can sort of tell our story of the network out got exceeded, and exceeded baseline bandwidth and was throttled. So we got slow communication, we got a drop in CPU, we start the replication lag, and then messages start to get back from the buffer, memory starts to climb, there's less messages sent, and then we hit that replica client output buffer overrun, and the replica disconnects from the primary and attempts to partially resync, fails its resync, and then it asks to do a full resync from the primary. Full resync is carried out the primary, which is tremendously expensive, and just the two things that are just most under load just get, even more so. And so even more memory is needed to take this snapshot. So, we've backed it all up with all these messages, and then we snapshot all that and send it over a heavily constrained network. And that just increases all the pressure on this node. And if we haven't already, we're definitely swapping by this point. And performance is just dropping. At some point in this, also the buffer client out buffer hits its hard limit, and that's when we start to see all of the those socket reconnections, because we're just disconnecting from the sockets. All those the spike of Redis connections, because everything keeps disconnecting and trying to reconnect. So if you think back to the responses that we did, we can kind of understand a bit why they had the effect they did or didn't. So we increased the number of target tasks, and we learned that the more tasks you have, the more messages you send. And if network's constrained, then sending more messages is not a good idea. So when we increased the number of tasks, it just made it worse. And when we reduced the number of tasks, if there are fewer tasks, fewer messages sent. So the network is less constrained. This is great. We reduced the frequency of those high volume messages, those mouse movements. That was great. So that was reducing load on our part of the constrained part of our system. This is interesting. When we failed over our primary, the replica that got promoted in its place is a new instance, and that has its own fresh, untouched burst capacity for us to abuse, and abuse it we did to recover. We kept turning things off and on again, which was pointless. That achieved absolutely nothing. And then finally, when we upgrade our instance size as our sort of early response, that did exactly what we feared it could do. Disguise the problem. It gave us a higher network baseline, and this was not something we were really paying much attention to, and we did not realize it was the exact fear that we had. And so the solution was, shocker, make it bigger. This time, actually make it bigger in a good way. Like, choose the right size. We know what we're optimizing for. We know what to monitor. We know what what we're choosing. What alerts to put in place. And so we can actually monitor this and do something effective. Like there's probably some questions somewhere of, should we just keep scaling this one big primary of our scalable system? Probably not. It's probably something we need to do at some point. But for now and at least for the future, this is we know how to deal with this. So things that you might take away. If you didn't know like me, that's really useful. That's interesting to know. And you know good how it works. We'd already had our dashboard set up, and we've already got everything ready to be able to see how our system's operating, and that was valuable. So as soon as anything went wrong, we could start looking into things, investigating, and so having that good visibility is really crucial. Equally, getting those automated alerts sort of told us immediately where to start looking, and the value of those well thought out automated alerts, I cannot overstate, because they're just incredibly useful. If you don't pay as much attention to baseline the burst as perhaps you should, do so. And also, this is an obvious one, but your answer is somewhere in the documentation. Redis AWS documentation particularly can be very awkward to hunt through, but the answer is there, which I will stress. The answer really is there. So when I go back and now I know what we're, what the exact problem was, I can almost point to the exact paragraph that describes in an embarrassing level of detail exactly what the problem is, what the symptoms are, and how to resolve it. And so it is there. So if we read it, everything end to end, line by line, perhaps we'd have spotted it, saved ourselves a bit of time. I have a pretty low opinion of technical support. I've rarely found them particularly useful, but they can be. So if you have a support plan, just use it. What's the worst you can do? And the thing that we learned increasingly is we're just going through, and building the system and operating it. Distributed systems are hard. There's lots that can go wrong, and there's loads of moving parts. And when you lay this out kind of like this, when I look back, it kind of seems really obvious where the problem was and why. But at the time, there's so much going on, so many moving parts, and any problem conceivably could almost be anywhere. And so I think when you have a distributed system, you introduce complexity. So make sure you need that complexity. That's it for me. Thank you very much. I hope you learned something, or at least were entertained with it. Thank you.
Happy to take questions.
I'm going to try.
Any questions?
So I think you kind of implied it in there, but so was Textbook able to tell you that you exhausted the network first time, despite it not having the metrics on the interface?
Yeah.
They obviously had some internal metrics.
They clearly have something. We just got unlucky or short-sighted by choosing the one thing that didn't tell us the immediate answer. But yeah, they were unexpectedly helpful in explaining sort of why everything went wrong and could tell us that, which is great. Yeah.
How big is your team in 2024? Like, how big is? Do you have some DevOps people or infrastructure people dedicated to AWS?
Not dedicated. It's more. I think we have like 20-ish engineers, ranging in some sort of T-shaped shape, where some people will have more front end, more back end, more infrastructure. So we don't have dedicated DevOps people. They're more relatively cross-functional teams.
Why did you take so long to look into logs for Redis? Like, there was clearly the message. In what point you realized that you could look into Redis logs and it will tell you maybe a little bit more?
What do you mean by Redis logs? Sorry.
Like, probably from my point of view, I would look into Redis logs immediately, or maybe in I don't know, several hours.
What do you mean by Redis logs? Sorry.
The log that you showed, like the network something. I don't really remember.
I mean, we did look at these things, but I mean, I think the fact that we couldn't get this metric that seemed to tell us the answer quite quickly, it kind of makes you sort of put it in the back seat and say, well, what else can we do? What can we find out now? And then you start looking at other things. So I think it's I think if we'd have been on a different instance type that had that metric available, we would have much faster got the answer. It was just terrible luck that we managed to choose the one that didn't give it this, because it was something we were looking for quite early, but we sort of couldn't get an answer. So it's like, we can't get an answer, what else can we look at? So we kind of tried to figure out some other things. And it was only kind of after a while, it's like, we could just ask AWS support. And it's like, what's the worst they can do? And then it turns out it's actually quite a lot good.
Thank you.
Did at any point you think it was like an attack or like service or something like that?
No. Good question though. Maybe we should have done. I mean, we have managed to almost do that ourselves by accidentally having a client that just bombards at the messages. So it's definitely not out of realms possibility that we could have do this ourselves. But no, we didn't. Any others?
Cool. Thanks very much.
Awesome.